Welcome back to part 2 of the Build Your Own Poker Bot series. In this video, we will take the counterfactual regret minimization algorithm and apply it to sequential games. And the game we're going to be solving in this video is Kuhn Poker. So what is Kuhn Poker? Kuhn Poker is an extremely simplified version of poker developed by Harold Kuhn in 1950. Just like regular poker, it is a zero-sum, two-player, imperfect information game. Imperfect information means we don't know what the other player's card is. And it's used by game theorists to help understanding how to solve imperfect information games. So the game is only 3 cards in the deck, and each player is dealt 1 card. There's no flushes, pairs, or anything. It's just the highest card wins. And in this version of Kuhn Poker we're going to be going over, there's no re-raising, so there's only 1 round of betting. Okay, so let's go over a game of Kuhn Poker. Starts it off with player 1. Player 1 has 2 options. They either pass or bet. If they pass, it goes on to player 2. Player 2 has the exact same options. Now if they pass, what happens is both players turn over their cards and the highest card wins. So we have a showdown. Now if player 2 bets instead, it goes back to player 1, and player 1 has 2 options, pass or bet. Now if player 1 bets in this situation, this is going to be the same as a fold, where player 2 automatically wins the pot. Now if player 1 bets, there's no re-raising, so both players turn over the cards and we have a showdown for the highest card wins. Okay, so now let's go back to the top of our tree, back to player 1. Now instead of passing, what's going to happen if we bet? It goes over to player 2. Player 2, pass or bet. If they pass, that's like a fold. Player 1 wins the pot. And if they bet, that's the end of the game as well. No re-raising. Highest card wins. So this is the game tree we're hoping to solve. And this is about as complex as it gets. And we'll be solving it with the counterfactual regret minimization. So let's review counterfactual regret minimization. So the first step we do is we select the action that we want to take. We calculate the reward we receive from taking that action. Next, we need to calculate the counterfactual rewards. And this is the rewards, other possible rewards we could have received from taking other actions. We subtract our counterfactual rewards from our actual rewards. And this is how we're going to get our regret. We're going to store all of our regrets into a table. Then we sum up, normalize our regrets, and then turn it into a strategy. And it looks something like this. So this is a possible regret table that we have. We have regrets for choice 1, regrets for choice 2, and 3. What we do is we turn these into a probability vector, and this is going to be our strategy. So 50% of our regrets were choice 1, and now we're going to choose choice 1 with 50% probability. So let's go over how we're going to solve Kuhn Poker using CFR. So we're going to run down the game tree. So let's just say player 1 passes, goes to player 2 bets, and it goes to player 1 passes, and they receive a regret of -1. Now what we've got to do is explore all the other actions that we could have taken in this state. So what would happen if we had bet? Well, in this particular hand, player 1 has a king, player 2 has a jack. So player 1 would have won the showdown. Now at this decision node, we're going to store our regrets. So in this example, we would get our regret for pass would be 0, and our regret for bet would be 3. So 2 minus -1 will give us 3. Now we don't stop there. We're actually going to take this reward that we got from passing, this -1 reward, and we're going to pass it up our game tree, and we're going to explore all the other things, all the other options. So, for example, we're going to explore what would happen if at the top of the tree we bet instead of pass. Now let's just say, for example, that player 2 instantly passes, then we would get a hypothetical reward of 1. Now we're going to pass up this hypothetical reward and use this actual reward at the bottom, and it's going to give us a regret of 2. So remember, our actual reward was -1. at this the top node were the pass, and our hypothetical reward for betting was 1. So 1 minus -1, it's going to give us a regret of 2 under bet. Now, as you can see, we're starting to converge at more of the optimal strategy. So if we dealt a king again, well, we're more likely to bet. And if we do get into this second node where we passed, we're not going to pass again. We're going to learn from our mistakes and then bet in that case. Okay, so just some final notes on CFR with Kuhn Poker, and we're going to go through what the code's going to kind of look like. So we're going to recursively go through the game tree, and when we reach a terminal node or when the game is done, we calculate the reward received. And we're going to do this for every action, and we're also going to calculate the regret for every action. Okay, it's something I didn't mention before. We're going to keep track of the probability of reaching each node. So for example, say our strategy is 50% pass, 50% bet. When we update the regret, we're going to keep track of the 50% probability of reaching that node. Another thing to note is we're going to update the strategies after each iteration, so after each game is played. So we're not going to update our strategy during when we're recursively running through our game tree. So once we run the CFR algorithm enough, we're going to land at a Nash Equilibrium that's going to look something like this, where we have our probabilities of passing and bet for each state we can be in. And this is going to represent a blueprint for our bot. So when a bot is handed the hand Jack, for example, it's going to pass with 80% probability and bet with 20% probability. And what's interesting is even in this simple Kuhn Poker game, we're starting to see some real poker strategies emerge. For example, with the Jack betting 20% of the time, why do we bet with the worst hand? Well, we're bluffing. So the bot has learned to bluff. And we can also see with King that it passes 5% of the time. This is slow playing. So we have the best hand where we're trying to induce a bet from our opponent. And then with King Bet, we have value betting, for example. And then we get the Queen Bet where we call some of the times. And what this is bluff catching, where basically our queen can only beat a bluff. So these are the strategies for player 1. Let's look at player 2. And it's kind of the same thing. So what we just covered and what we're going to go over in the code is what's sometimes called vanilla CFR, or the very simple CFR. Now this is going to work great for a game like Kuhn Poker, which is very small, scale up poorly in larger games like No Limit Poker, Texas Hold'em. One of the problems is it's very memory intensive. Vanilla CFR models can hit over 215 terabytes of memory, and it's also inefficient in some of its path. It can take it can take millions of core hours to compute. And we're going to improve this in 2 ways. One way is by using CFR Plus, which is an improved version of CFR. And we're also going to use MCCFR, which stands for Monte Carlo Counterfactual Regret. And we'll also be covering pruning, which is used to not explore some of the worst options in the game tree. Another thing we got to do is go over abstraction, and this is going to be used to reduce the size of our overall game tree. We'll be covering these topics in future videos, but for now we're just going to be going over the code in vanilla CFR. Okay, so let's start off by looking at each node. And now each node is going to look very similar to the rock, paper, scissors one we just did, and that's because most of the code was copy and pasted. But we have the same thing, the get strategy, get average strategy, and print out the string. The only difference here is we have this reach probability, and remember that's the probability we have of reaching this node in the game tree. And we also have this update strategy, and this is run after each iteration of the Kuhn Poker game. But other than that, it's the same thing as the rock, paper, scissors. This is for each node on our game tree, remember. Okay, so let's go over our CFR function. Now this is a recursive function. We're going to be recursively calling it. So we got to make sure we have our terminal state of when we end it. And this is simply all the states we could have that would be the end. So both players pass, both players bet, or there's a bet and then someone passes. So those are all the options. Next we have our get reward. And basically for each time there's a showdown, we determine which card has the higher value. And if not, someone passes, we just give them a reward of 1 for the winner of that. Okay, so here's up to here. Now what we need to do is determine which node we're in, and we use with this get node function. And the key for the node is going to be the player card plus the history we're in. So the history will look something like Jack, and then there's like a bet and pass or something like that. We get the strategy from the node, and then we're going to recursively call this CFR function, and this is going to return us the reward. We do up here. Now each time we go up the game tree, we're going to multiply it by -1, and that's because if player 1 has a reward of 1, player 2 will get a reward of -1 for losing the game. So every time we go up the step, we're going to multiply it by -1. We're going to store it in this vector. Now to calculate the regrets, we're going to sum up all of them and then subtract each individual action by that total reward at that decision node. Okay, and then lastly, we update the reach probability and then the regret sum. So we have our regrets here, and we're going to sum it up in our table for each node, remember, multiplying it by the probability of reaching that node. Okay, and when we run this, about 50,000 times, I guess, there we have our Nash Equilibrium. So the actual value is supposed to be 1/18, which is about 0.005 or 0.5. So it's pretty much similar. And then we have the perfect strategies, or the optimal strategies for player 1 and player 2. Okay, so that's all for today. Thanks for watching.